into as small a part of as simplified, I suppose, factors as possible. Okay? So I want to factor this. What can I do first?
Long division.
No division to be done.
Could divide it by 2.
You can factor out 4, right? You can pull something out from each one of these, do that first. So you're left with that's right.
Yep. Oh, this is
I am. That was a good one.
brilliant.
Friday. All right. We need to factor this as far as we can as well. So what goes here and here? X squareds. X squareds.
We got a plus and a minus.
We have a plus and a minus. We don't have a plus and a minus.
I'll get a minus and a minus.
Plus or minus. We have a minus and a minus. Nine and 5, right? Jake, are we all right with that one? Okay. Now you're probably asking, hey, 4 isn't prime.
It's not prime.
The factorization is a little bit different with polynomials versus just numbers. What I'm trying to do here is to break this down into as small factors as possible. 4, there's nothing else we could do with 4. I mean, yeah, we could write it as 2 squared, but 4 is fine. What I want to do is take these factors and break them down as small as possible. This is a multiple, but it's still a constant. It's okay. So constants are fine.
X plus 3, X minus 3.
So we've got x plus 3, it's still plus and minus. X plus 3, x minus 3. That one we clearly can break down. By the way, just as a side note, not that you were going to think anything different, but this is over the reals. You could factor something over the complex numbers, which are going to give you imaginary roots, which we can do later in the year.
But that's not going to
No, we can't.
X squared minus 5. Can we break that down anymore?
We can't really do a whole lot with that.
You can. What is it going to be broken down into? Square root of 5. Okay. Now there's nothing else we can do. We've got just simply x plus square root of 5, x minus square root of 5. There's nothing else we can break down or factor out. And that would be your, that's your prime or your unique factorization for that polynomial. Yeah.
So you wouldn't do just like 2 squared?
You could, don't worry about that though, yeah. You could, I wouldn't mark it wrong, you don't have to. Yeah. Yep. Yeah, these numbers themselves aren't what we're talking about when we say prime factorization of polynomials. We're saying break it down into as small parts as possible. Yeah, we want to break it down as small as we can, even if they're square roots. Here's an example of something you cannot factor. This is prime. That's prime. Why is that prime?
Because of 1.
Because it's plus 1.
Plus 1. If you were to factor this, you're going to get imaginary numbers. That's not over the reals. So this is a prime factorization. That's done. You can't do anything else with it. But this one, we could break down as far as...
If it was minus 1?
If it was minus 1, then you could x minus 1 times x plus 1. Okay? All right. The proof, and we're done.
Oh, bow rod.
Woo.
His phone does not have that much battery.
Yeah, I got like 2 gigs left storage.
This one's not too long.
Our proof's gonna be on the test.
Yeah, well, I started with 7.5.
Those are so hard.
You just download it and then just
Okay, on your proof sheet, you have to prove there is no largest odd integer. So we're going to prove there is no largest even integer. That should make your proof worksheet a little bit easier. We're going to do this by contradiction. So this is a proof by contradiction.
So, wait.
How much space? Oh.
Nope, still a proof.
T.
It's a different approach.
Just contradicting itself.
How much is this? Is this enough space?
Yeah, if you write small.
What does it mean? Prove there is no largest even integer.
So prove that
I can.
if you the number 4 isn't the largest even integer. There's always another one. 6, and there's 8, and 10, and 12.
Oh, just in general.
And, yeah. Okay, so we are going to suppose there is a largest even integer. This is how we start all of the contradiction proofs. Suppose the opposite. This is what we wanted to prove. Suppose it's the other way around. There's only 2 options. It's either there is a largest or there isn't a largest. So suppose there is a largest even integer. We can call this, how are we going to define an even integer? How have we defined that? Yeah, so we can call this 2, I'll stick with k because we've been using k. So 2k, as long as k is an integer. So we suppose there is a largest one, we call it 2k. Okay. Here's the somewhat nuanced part. What can we do with any number? We're talking about there isn't a largest one, or there is a largest one, but any number we know we can do what with? Yeah, we can add something else. And in this case, we're going to add 2. Why do you think maybe 2? It's going to get us to another even number. If you have an even number, you add 2, you're back to another even number. So, add 2 to 2k. Now we have 2k plus 2.
Sounds like a lot of range.
We're almost done.
Oh, seriously? You told me to write small.
I didn't mean that small. Now we have 2k plus 2. Can we make 2k plus 2 look even? What's an even number look like? Yeah. Even number always looks like 2 times an integer. Can we make that look like 2 times an integer? I heard some people say it.
Yes.
Factor that out. 2 times an integer, right? We know that k is an integer, so k plus 1 is an integer by your favorite thing, closure. Thus, 2 times k plus 1, I don't think I've been putting it. 2 times k plus 1 is even by definition. Thus, 2k plus 1 is even by definition. We have a contradiction. What's the contradiction? Yeah, we said 2k was the largest, but wait, 2k. There's a 2k plus 2. That's larger. So we've shown that is not true. There's a contradiction, and therefore, if that's not true, the only other thing that could be true is what we wanted to prove. So we have a contradiction. Therefore, there is no largest even integer.
Wait, what's the contradiction?
Yeah, do we have to write what the contradiction?
Well, we stated it in here. you don't have to rewrite it. The contradiction is that we suppose there was a largest even integer called 2k. When we had 2k, we added 2 to it. That's legal, right? You can add 2 to any number. When you added 2 to it, that number we also showed was even. So we said 2k is the largest, but then we found 2k plus 2 times k plus 1 was larger and even. That's the contradiction.
So on the homework when it's like prove, what was the one? Prove there.
The one that we have in your homework is prove there is no largest odd integer.
So you would add 1.
So it'd be 2k plus 1, and then you're going to add 2 to that number as well. Alright, I've got a review packet if you would like. It's optional.
Got the answers.
I do have the answers.
Are you done?